Okay, so hello, good evening. Welcome to the PMRF NPTEL session for the course Signals and Systems. This is week 8 Signals and Systems. So just hold on for a second. Okay, so hello and good evening. Let's continue. I am Shouharda Ghosh, second year PhD scholar in the Department of Electrical Engineering. This is week 8 of the course Signals and Systems. So let us first quickly state the topics that we have learned in the week 8. So let me write them over here. Laplace transform, linearity shifting, Laplace. Okay, so it was all about Laplace transform, where we had linearity, causality, shifting, scaling, and all these similar properties were studied. Then we also looked at derivative and integral of a signal. These properties were also looked at. Then Laplace analysis of second order circuits were also carried out. So it's just simply the continuation of the Laplace transform which we had done in the previous week. So we'll just solve a few problems and that would be it. Okay, so let's move into the first question. The first question states that we are given two signals or two Laplace transforms, x1s which has 1 upon s plus 1, x2s which is 1 upon s plus 1 times s plus 2. Okay, and we are given that y of s is x2 of s minus x1 of s. Now it's also given that y of s is causal and stable. Now what do we need to do? Find ROC of y of s. Okay, so let's look into it. Let us initially find what is ys. Ys equal to 1 upon s plus 1. Okay, so actually this is x1 minus x2. So this is 1 upon s plus 1. This is 1 upon s plus 1 times s plus 2. Simplifying it, s plus 1, s plus 2. We have s plus 2 in the numerator minus 1. This boils down to s plus 1 times s plus 1 times s plus 2, and it gets simplified to 1 upon s plus 2. Okay, so let us draw the poles 0 plot. So you see we have only single pole, that is s equal to minus 2. Okay, this is a pole. Now there are two possible ROCs as we had learned in the previous class. One is the ROC to the right of this, let me call that ROC1, and the other one is the ROC to the left of minus 2, and I call that ROC 2. Okay, now what do we want? We want causal as well as stable ROC system. So what does causality imply? Causal means that ROC is right sided. And what does it mean to have a stable system? The ROC must include j omega axis. So which of these properties are satisfied? Which ROC satisfies this property? As you can see, this is ROC1. So in other words, how can you write ROC1? So everything that is to the right of this plane. And what is this plane? This line is sigma equal to minus 2. So anything over here is greater than minus 2. So sigma greater than minus 2. So our ROC is sigma greater than minus 2. Okay. So this is the ROC for y of s. Alright. Now let's look into the second question. And 2. So we are given that y of t is x of t minus 3 and x of t is cos omega t ut. Now we have been asked to determine Laplace transform for y of t. How do we approach it? Okay, so here we look into the general property. Let's see if I had covered this property earlier or not. Okay, so we had just started the Laplace transform, so no properties were covered. Fine. So if we have a signal, let's say x of t, whose Laplace transform is x of s. Alright. Now let us suppose we shift this by an amount tau. What will be the new Laplace transform? Let's evaluate. So x prime s, don't confuse it for a derivative, is integral x of t minus tau e to the power minus st dt. So how do we proceed? I proceed by multiplying e to the power minus s. I write this kind of a term, and then I write this term because they cancel. This e to the power minus st and e to the power st will cancel each other, this and this. D. Now dt, this is very simple algebra, is dt of t minus tau, and this is essentially a constant because the variable is dt. So I can take this out and I substitute t minus tau as z. So I can write x of z e to the power minus s of z dz, and this is essentially our Laplace transform x of s. Okay, so what do we conclude? X of t minus tau as a Laplace transform e to the power minus s tau x of s. Alright. Okay, so that was the shift property. So now this is a bit easier. Now we are given that yt is x of t minus 3, so we can directly write y of s will be e to the power minus how much? 3. The delay is 3. E to the power minus 3s to x of s. Alright. So now what is x of s? We have xt as cos omega t ut. Now if you remember, I had asked you to solve this back in the homework in the previous lecture. We found that xt was x s whose Laplace transform is x of s, which is s by s square plus omega square. Okay, so what is our y of s? Our y of s finally turns out to be e to the power minus 3s s by s square plus omega square. Alright. Fine, so this is our answer for the Laplace transform y of t. Let's look into the next question. We are given x of t is sine omega t ut and yt is x of 0.5 t. Now we have been asked to determine the Laplace transform of yt. So again we will start first define the property. Okay, so we will first define the property and then we will find the actual numerical in this form value. Okay, so let's say you have a signal xt once again whose Laplace transform is x of s. Okay, so now we are supposed to find the Laplace transform of the scaled value of this signal. Alright, so x prime s is the normal integral x of at e to the power minus st dt. Okay, so now what do I do? Let me substitute z equal to at or t equal to z upon a, which implies that dt is 1 upon a dz. How do I replace that? X prime s is integral minus infinity to infinity x of z e to the power minus s a z dz upon a 1 upon a integral minus infinity to infinity x of z e to the power minus s of a z dz. This is once again a Laplace transform when the Laplace s variable is replaced by s of a. So I can write it as 1 upon a x of s upon a. Okay, so that means that x of at will always have a Laplace transform 1 upon a x of s upon a. If you remember, these properties are exactly similar to the one, or almost similar to the one that you have studied in the Fourier Fourier transform. Okay, the Fourier, because actually Laplace transform is a more generalized version of the Fourier transform. Of course, some of the properties may be different, but in general, a lot of them will resemble similar. Okay, so we have been told that y of t is x of 0.5 t. So what would that mean? That would mean that y of s is 1 upon 0.5 x of s upon 0.5. That boils down to 2 into x of 2s. What is xt? Xt is sine omega t ut. Okay, x of s, if you remember, I had derived in the previous class, that was omega by s square plus omega square. Okay, so now what will we do? We will simply substitute ys equals to 2. Now I will substitute s by 2s. 2 omega by 2s square plus omega square, that turns out to be 2 omega 4s square plus omega square. Alright, so our ys over here is ys is 2 omega 4s square plus omega square. This is the answer. Alright, so now some other questions, easier ones, but before that let us look into some other properties. Okay, so we have done linearity is quite obvious because a into x plus b into y, that's something common that we have dealt with. So we have done shifting and scaling. Let's look into derivative first. So let's say you have a signal xt whose Laplace transform is x of s. So what would be the derivatives Laplace transform? Let that be x prime of s. Okay, so you see x of s is integral minus infinity to infinity x of t e to the power minus st dt. Okay, and as an alternate formula, the integral xt is 1 upon 2 pi j integral. Let's ignore all of these integrals. I will in all of these values, I mean the form of the integral is not important over here, the internal values are more important. So we are just approaching it in the Fourier transform way. So what will we do? We will differentiate this. Dx of t dt is d dt 1 upon 2 pi j. This is the contour integral sigma minus infinity sigma plus j infinity x of s e to the power st ds. So what will end up getting differentiated? Xs is not a variable of time, d dt of e to the power st ds. So when you when you differentiate that, s would come out. So you have s xs e to the power st ds. So what should we get? We will be getting this. So dx of dt will have a Laplace transform of s into xs. And if you want to generalize it further, the nth derivative of xt will have a corresponding Laplace transform of s to the power n x of s. Alright, and for the case of integral, if you look at integral infinity to minus t x of tau d tau, if you look at this form very carefully, you can always express it as the convolution between x of t and the unit step function. Alright, and although I believe that to you, we know that the Laplace transform of the unit step function is 1 upon s. Okay, so, and another important fact that convolution in time domain leads to multiplication in the Laplace domain. Okay, so if we use that, and let's say let me keep xt as the same, yt as unit step, then the Laplace transform is x of s upon s, because unit step function has the Laplace transform of 1 upon s. Alright, so the integral of a function, let me write it in a better place. Integral of a signal over time gives a Laplace transform xs upon s. Okay, so this was differentiation and this is integration property. Okay, so now let's look into a few more problems. So we are given that this is our ROC j omega plane, and we have a pole at A, and note that A is greater than 0. So what will we do? We will draw a straight line through it, and we have been told that the ROC of the system is like this. This is the ROC. So what kind of a system is this? Let's look at the nature of the signal one by one. The signal points to the right side of A. Okay, this is the right and this is the left. We see that it's towards the right side. So right sided implies that the system is causal. And does the ROC intersect the j omega axis? No, right? So it does not intersect j omega axis, and this implies that it is causal and unstable. Okay, so it's causal because it's right sided ROC, and it's unstable because it does not include the j omega axis. Okay, so we discussed that in the previous class as well. Now one more final question on ROC that will revise everything. So this is one pole and the corresponding ROC. This is another pole and another ROC, and here you have got the second ROC. there are, this is ROC1, ROC2, ROC3. Alright, so 3 ROCs are there. Now we need to determine the causality and stability of these ROCs. Let me write that down. ROC, causality and stability. 1, 2, 3. Okay, so if I give a tick, that means it will be causal or stable, and if I give a cross, that means it will be anti-causal or okay. So I won't give a, I will use abbreviations rather, because there is causal, anti-causal and non-causal. So let's look at ROC1. Is ROC1 left-sided or right-sided or something else? You see, it's clearly left-sided, and when it's left-sided, it's always clear that it will be, the signal will also be left-sided, and when the signal is left-sided, it's supposed to be what? It's supposed to be anti-causal. So 1 is anti-causal. And does ROC1 intersect the j omega axis? No, right? It doesn't intersect the j omega axis. So what will happen? It will be unstable. Let's look at ROC2. ROC2 is a bit interesting. It's neither left sided nor right sided. It's a vertical strip. So what will happen? It will be existing towards the left side as well as the right side. Okay, so it will converge for both sided signals. The integral will converge for both sided signals, and that is why the causality will be non-causal. And let's look at the stability. Does it once again include the j omega axis or not? See, simply no, the j omega axis is outside, so it's unstable. Now let's look at ROC3. ROC3 is right sided, so it's causal. And if we look at the stability, it does include the j omega axis over here, so it's obviously stable. Okay, and you can even solve cases where the j omega axis is over here. In that case, what happens? In that case, everything remains same except that this one becomes stable and this one becomes unstable, because ROC2 includes the j omega axis and ROC3 does not. Okay, and I may even move the j omega axis over here, or the system may be such that j omega axis is over here. So what will happen over here? Here this will remain, all these things will remain the same, but this will become stable because this includes the j omega axis. This one will remain unstable, and this one will also become unstable because this one is over ROC1. Okay, so this is my last discussion about ROC, because we have discussed a lot about ROCs in this one as well as the week 7. If you have seen this week 7 lectures, so I had discussed in great detail. I mean, we had even derived how left-sided means anti-causal, or how right-sided means causal, and all that thing. Okay, so you can refer to the earlier lectures in order to revise these concepts, and of course the course lectures as well. Okay, so yeah, so in fact somebody may give you some question regarding some circuit may be given, and then in reality what happens is that in the circuits are all positively valued, so the corresponding roots of the poles of the system turn out to be negative towards the left hand side. So because real circuits won't give you unstable systems unless you have certain active transistors in it which may modify the poles of the system. Okay, now let's look. So we have a system whose impulse response h of t is 3 e to the power minus 2t minus 2 e to the power t ut. Okay, so what will its Laplace transform be? So we have a 3 e to the power minus 2t over here, and a 3 e to the power minus 2t term will decay like this, and minus 2 e to the power t will go down like this. So the net thing will be something like this. So 3 e to the power minus 2t ut has a Laplace transform of 3 upon s plus 2. 3 upon s plus 2, right? So 3 upon s plus 2 means it will have a Laplace, it will have the region of convergence real part of s greater than minus 2. Okay, it will be something like this. And then we have minus 2 e to the power t ut, whose Laplace transform will be minus 2 upon s minus 1, which means that real part of s will be less than 1. Okay, real part of s will be less than 1, which means this is 1, this is this. Okay, these are the separate ROCs. Now let us combine them. We have the poles at minus 2 and 1. So we have been asked to find the region of convergence so that the system becomes okay, unstable and anti-causal, stable and causal. No, it can't be causal. Let me solve this in front of you. This is the last question. So what are the possible ROCs that we can draw? So the first ROC will be over here, sigma less than minus 2. What does that become? That makes the system unstable because j omega x is excluded, and causal, anti-causal or non-causal? It's anti-causal because it's toward the left side. Anti-causal. Let's look into the middle one. Minus 2 like sigma to 1. It's stable because it includes the j omega axis. It's non-causal because it's a strip. And the final one, sigma greater than 1. This is what? This is still unstable because it excludes the j omega axis, but it is causal because it's right side. Unstable but causal. Okay, all right. So these were the set of questions I had for this week. I mean, it's a bit short because I've taken the questions from the previous year assignment. So things are quite repetitive and simple now because a lot of these things have already been covered in the Fourier transform. So all of these are just an extension to whatever you have learned over there. So if you have any doubts, you can ask in the forum section. All right, I hope you enjoyed the session. Thank you. Have a nice day.